Let's just get started. So let's recap a couple of definitions from a few videos ago. We have a statistic, which is something that describes a sample, such as the sample mean or the sample median. And then we have parameters, which is a characteristic that describes a population, so the population mean. Descriptive statistics uh, is where we collect data and then we organize and summarize it. Okay, so for example, we'll take a sample, we'll measure their blood pressures, and then we'll find the mean. Okay, and that will be a statistic. That's descriptive statistics. And then in inferential statistics, we're going to take that data and then we're going to use it to describe the entire population. Okay, so let's talk a bit more about inferential statistics. So, in inferential statistics, what you'll do is you'll take a sample, and then you'll study the sample, and then you'll use that sample, and you'll use the information that you got to infer stuff about the population, to basically say, hey, this is what we've learned about the population. And in inferential statistics, you look at two things. First of all, you look at, is the conclusion that you got when you measured info from the sample, is it true or not? But because you can't know for sure, you can't know for 100% if it's true or not from just an experiment. Instead, what you're going to do is you're going to try and see if it's probably true. Like, what is the chance that it's true? And the second thing that we look at in inferential statistics is how likely are you to get the same results if you repeat the experiments? Okay? So let's look at why we study probability. Well, obviously, if you have a gambling addiction, studying probability will help you do it more efficiently. Okay? And when you study probability, you can get really, really good at making inferences. Okay? Which, let's be honest, you're probably not really going to do much of as a doctor. But hey, I don't care. And finally, let's just take a look at the sample picture and recap everything all over again before we move on. You're going to take a sample, you're going to find data, and you're going to use descriptive statistics to describe this sample, and then you're going to use inferential statistics to apply the data that you got to the population. So, when you do samples, it's affected by random variation. Alright, when you take a sample, your statistics will get affected by random variation, which is basically where the sample is random, and so the sample will change every time that you collect it, and you're probably not going to get the same people each time. And because of that, your data will change each time, and your statistics will change each time. And so we can use probability models to look at the probability of certain stuff happening, and then we can use those, and what that means is that we can look at the sample and we can see how likely was it that the sample is actually good and representative of the mean. Okay. So, for example, so let's just recap this example for a probability model. There's the odds of developing cancer, and it's influenced by many factors. These are the factors over here, and we write it out using y plus x1 plus x2, and e, which is your error. Okay, now, as I'm probably sure you're starting to get used to this, which is the fact that BEP is actually just an undercover operation to prepare everyone for a long spelling bee. So here's more definitions. A probability is the tool that we use to study uncertainty. And an experiment is a procedure that has outcomes. Okay, pretty straightforward. Such as flipping a coin. And then we have an event, which is represented by E. And an event is an outcome that happens in an experiment. And we can apply a probability and probabilistic equations to look at this event. All right? So events are usually represented by uppercase letters, okay, such as A, B, C, P, Q. And then we have simple events, which will only have one outcome. Okay, so for example, when you roll a dice, you could get an outcome of 3. So I might make an event to look at how likely am I to get a 3 when I roll a dice. And the event, which is rolling a 3, is a simple event. But if I want to look at rolling an odd number, there are 3 outcomes where I roll an odd number. So, rolling an odd number is not a simple event. And finally, we have the sample space. Okay, now a sample space is just a set that has all possible outcomes. It's a set that includes all simple events. So let's take a look at a bunch of equations and a bunch of math stuff. First off, we have union, which you can see here in the Venn diagram, and it's represented by this U shape. So union basically says that it's the event of A, the event of B, or the event of both. So here you can see that we have the event shaded in green. So A union B, you have both A and B shaded in, and both. And in the intersection, which is represented by the upside down U, it has to be both A and B. Okay, so here you can see on the Venn diagram, we have in the second one, we have only the point where it's both A and B shaded. And finally, we have the complement, which we represent using this small c up here, which basically says not A, right? So the complement of A is not A. And so here in the Venn diagram, you can see that everything is shaded green except for the A, except for the circle for A. All right. And here's a bunch of other Venn diagrams. I included the citation here so I don't get sued by the people that made it. We have the union, which we already spoke about. That's event A, the circle for A, the circle for B, and including the area of both. The intersection, which is only both A and B. And then we have the union minus the intersection. And so it's A or B, but not both. Then we have the complement of A, so everything is shaded outside of the circle for A. Okay, and then we have the intersection of A and not B. Okay, so this circle is A. All of this area is not B. Actually, let me start using a pen for this. So this area is A. Right, this circle. And if I change the color, all of this area, all of this area outside here, including the inside of A, is not B. And so if we look at the intersection, which part is both inside A and outside of B, that's this area over here. A bit shaded. Okay? And then in the next example, we have the exact opposite. We have not A, so all of this area, and inside B. And B, so so it's the area that's both outside of A and inside of B. So inside of B is this circle, and the part of the graph that's both outside of A and inside of B is the part that's shaded here by the picture. I drew something that looked like a rabbit. And then the next example, we have the union. And so it's either A, which is this circle, or it's B, or it's not B. And so let's change the color again. Let's make it blue this time. And so not B is all of this area that's outside of circle B. And so if we combine those two and we shade all of it, then we get the union of A and not B. In the next example, we have Just a second. All right, so in this next example, we have the union of not A and not B. Okay, and another way of writing this is the complement of the intersection. Right, so not both. So everything that's not both is shaded. And then the final example is the intersection of, and so it has to be both not A and not B, or it's just neither, and so everything outside is shaded. So let's look at how you can write probability, mathematically. And so so here we have the notation for the probability of event A. Okay? And so again, just bear in mind that this will be written from 0 to 1, either in fractions or in decimals. Okay? And so in practice, the way we can find the probability of A is we do an experiment a whole bunch of times, and we look how many times does A happen. And then we divide the number of times that A happened by the number of times we repeated the experiment. So let's take an example. The probability of you dying, well, you're definitely going to die, so that has a probability of 1, right? Meanwhile, the probability of you achieving anything meaningful, well, that's never going to happen, so that has a probability of 0. Okay, and finally, the probability of getting a 20 on a 20-sided dice, well, that's 1 out of 20. Okay, and if you write it as a decimal, you convert it, it's going to be 0.05. All right, and there are 2 rules when you write out the probability. It has to be between 0 and 1. Okay, it can't be more than 1, it can't be less than 0. Well, unless it's like the elections in basically any country, in which case it's probably rigged and the odds are slightly higher than 1, but oh well. Now, the probability of S, and S, if you go back a second, S, that's the sample space. So the probability of S, or the sum of all of the events, their probabilities put together, that's always going to be 1. That has to be 1. So how do we find the probability of A? Well, like I said, in practice, we can just do an experiment a whole bunch of times. Or another way is that we can list the sample space, right? And so we can list everything that could possibly happen, and we can see how many times does A happen in the sample space. So let's take an example. We have a coin toss. Now, coin tosses will have heads or tails. Yeah, I know they can land on their side, but let's ignore that for now. Right, like, come on, let's make things easy a bit. Okay, so let's throw a coin twice and find the probability of getting heads twice. So here we're using H to represent heads, T to represent tails. And so when we write it out, we need to find the probability of double heads, the probability of HH. Okay, so we write out the sample space over here, so we can get double heads, heads and then tails, tails and then heads, or we can get tails, tails, right? And so there are 4 outcomes, and heads twice happens only 1 time, and so the probability of getting heads twice is 1/4 or 0.25. Okay, let's take another example. 500 students join every year. Okay. Yeah, 500 students join every year, and I stabbed 20 of them. Okay? Find the probability of not getting stabbed. So if I stab 20 students, that means the number of students not getting stabbed every year. Well, that's going to be 480. Okay, and then 480. Okay, so you're going to be one of those 500 students. And so there are 500 outcomes. Either you're one of the 20 that get stabbed, or you're one of the 480 that don't. And so 480 divided by 500, which is not getting stabbed, well, that's 0.96. So you have a 96% chance of surviving. Oh, and by the way, since we're eventually going to get a psychopath that does actually stab people in this uni, police, I don't go around stabbing people normally, okay? This video is not enough evidence to try and convict me. Leave me alone, don't come to my house. Anyhow, so let's look at some more rules for probability. Let me get rid of this pen so I can see the cursor again. Actually, let's use a laser pointer, let's be fancy. So, the intersection of A and the complement of A, or A and not A, well, that's the null event. And the null event basically means that in these Venn diagrams that we used to shade, the intersection of A and not A, well, we don't shade anything. We don't shade anything because we don't shade anything. And so the probability of getting both A and not A, well, that's 0 because you can't get both A and not get A. Right? The second rule is that the probability of A is equal to 1 minus the probability of its complement, or 1 minus the probability of not A. Alright? So, if event A and event B can't happen at the same time, we call that mutually exclusive. For example, event A could be rolling a 1 on a dice, and event B could be rolling a 6. And since you can't roll, so if you roll a dice once, you can't roll both a 1 and a 6. So the intersection between these two is the null event again. And the probability of rolling both a 1 and a 6 is 0. Okay, now the next one is this notation, which is the probability of A given B. Alright? Or the probability of A if B's already happened. So, for example, the probability of A could be you getting shot, okay? And then the probability of B, event B, is you annoying some mafia person, right? And so the probability of A given B is the probability of you getting shot if you annoy a mafia person. All right? Now, if A and B are independent, or if A and B don't affect each other, then the probability of A given B is the same as the probability of A. Right? So, for example, if A was you getting shot, but this time B was you drinking coffee tomorrow, right? Well, you drinking coffee isn't going to affect how likely you are to get shot. Okay? So, the probability of you getting shot if you drink a coffee is the same as the probability of you getting shot normally, which I should hope is pretty low. Okay, so just to be sure, independent and mutually exclusive aren't the same. Let me explain. And it's not okay. So when we have mutually exclusive events, when A happens, B can't happen. And so the probability of A given B, or the probability of getting B if A has happened, is 0. And the probability of the intersection of A and B, so both A and B, that's also 0. Okay, finally, the probability of the union, so either A or B, that's just the probability of A plus B. Okay? Now, if they're independent, okay, B doesn't care about A doesn't care about B. Neither one affects the other. Okay? So the probability of B given A, that's just the probability of B, it doesn't change. The probability of the probability of the intersection, so the probability of A and B, that's the probability of A times the probability of B. Okay? So, for example, the probability of you both getting a heads and a 3, right? So that's 1 over 2 multiplied by 1 over 6 to get the probability of both. And finally, the union, we're going to look at that in a little bit. Okay? So, we have a couple more rules. We have the additive rule, first of all, which is when you want to find the union between two events, and you want to find that probability. Okay? And so, the union is the probability of the union is the probability of A plus the probability of B minus the probability of the intersection. And the reason for this is if we go back to this Venn diagram over here, is that if you look at the union, okay, it includes the intersection. But if you add the probability of A and the probability of B, you're going to end up counting it twice. And so when we do the additive rule to find the union, you add the probability of A and the probability of B, and then you want to subtract this intersection over here so that you don't count it twice. Okay? And then we have the multiplication rule, which we use to find the intersection, which is the probability of A multiplied by the probability of B given A. And we can also flip this, so we can have the probability of B multiplied by the probability of A given B. Okay? So, if A and B are independent, then the probability of B given A is just the probability of B. And so this intersection changes, and instead it's the probability of the intersection for these two independent events becomes the probability of A multiplied by the probability of B. All right? Let's take an example. So, find the probability of getting a heads in a coin toss, or rolling a 3, or both. Okay? So basically I'm asking for the union. Right, so let's write it out here. I chose H for heads, and the number 3 for rolling a 3. So the probability of the union equals the probability of getting heads plus the probability of rolling a 3 minus the intersection. Okay? And now let's apply. Okay, so let's apply the multiplication rule over here, and so this becomes this. All right. So the probability, so the probability of the intersection becomes the probability of heads multiplied by the probability of 3 given heads. Okay. But because these two events are independent, right, tossing a coin and rolling a dice won't affect each other. That means we can just make it the probability of heads multiplied by the probability of 3. All right. So let's replace everything by their numbers. Right, so the probability of getting a heads in a coin toss, that's 1 out of 2. The probability of getting a 3 when you roll a die, that's 1 out of 6. And so we have 1 over 2 plus 1 over 6 minus, and then we open the brackets and over here, 1 over 2 times 1 over 6. Okay? And so 1 over 2 times 1 over 6, that's 1 over 12. And then if you plug this into a calculator, you'll get 0.558333. All right? So let's take another example. The probability of getting rain is 5%, and the probability of that I wear a hoodie is 80%. Now for this case, let's assume that they're independent, mainly because I don't actually look at the weather, so whether or not it rains, I might wear a hoodie, I might not. Nothing really changes. Okay. And I've lost my cursor. Okay. So find the probability that either happens. All right, so we have the probability of rain, that was 0.05. The probability that I wear a hoodie, that's 0.8. Okay, and our probability of rain, that's R. Probability of hoodie, we've decided to make it H. So the probability of the union is equal to the probability that it rains. All right, so the probability of the union is the probability that it rains plus the probability of me wearing a hoodie minus the probability of the intersection. Okay, so let's put the numbers in. Probability of rain is 0.05. The probability that I wear a hoodie is 0.8. And then we still have the intersection. Okay, so let's find the intersection. The probability of... All right, ما حدا شاف. Okay. So the probability of the intersection is the probability that it rains multiplied by the probability that I wear a hoodie given that it rains. All right? Again, they're independent. So it just becomes the probability that it rains multiplied by the probability that I wear a hoodie. Or 0.05 multiplied by 0.8, that's 0.04. Okay? And so let's put that back into here, and we end up with 0.05 plus 0.8, okay, minus 0.04, that'll be 0.81, okay? So this whole, like, given thing, right, for now, like so far, we've talked about independent events and mutually exclusive, right? But what if it isn't like that, okay? And so the key thing is that events will influence each other, usually, right? So for example, how many hours you're able to study today will get affected by whether or not you drink coffee in the morning or whether or not you have breakfast and stuff like that. All right? And so we want to look at this stuff because it can influence diseases. So for example, the probability of... Where's my... So the probability of dying from a shotgun to the head, that's 99%, right? Which is actually surprisingly low considering it's a shotgun. And the probability of appearing on a late night show and eating bullet-shaped nuggets, well, that's pretty low, right? Like that's going to be less than 1%. But the probability of appearing on a late night show and eating bullet-shaped nuggies, if you do survive a shotgun shot to the head, well, that's going to be like a lot higher because, you know, they're going to want to talk to you and find out your secrets to surviving shotguns, right? And obviously this was a joke example, but this is actually pretty important because when we look at a medication, we want to see how much more likely is the patient to survive